And today I will talk about biodegradable self-assembled polylactide block polyethylene glycol copolymers and their applications for delivery of anti-cancer drugs. First, I'll do a quick introduction, then we'll talk about synthesis of linear and star-shaped polymers because, well, synthesis is a crucial part in order to prepare well-defined particles and in a controlled manner. And then I'll switch to our results on studying the effect of composition of such a diblock copolymers on the size and structure of nanoparticles using various methods of investigation. And then in vitro results and some preliminary results of in vivo experiments. Okay, let's start with the introduction. I think all of you know the opportunities which are offered by nanomedicine. A lot of anti-cancer agents are great, but they are not specific and have high toxicity, non-selective action, side effects, poor solubility, short circulation time, and by creating a drug delivery system based on nanosite polymeric structures, particularly polymeric. Actually, there are a lot of plenty of various nanocarriers, but today I will talk about polymeric nanoparticles. So by loading the drug inside or on the surface of a nanoparticle, we can achieve a specific delivery to the target tissue, particularly to the tumor, through the passive targeting, which is realized by the well-known PPR effect. I'm sorry. And also through the conjugations of the ligands on the surface of the nanoparticle, which helps to the particle to recognize the cancer cells. These systems are usually characterized by improved circulation and improved time of circulation and improved pharmacokinetic profile and lower toxicity. So we are focused on various biodegradable polymers in our laboratory, particularly polylactides, some copolymers with glycolide and caprolactone. And today we'll talk about amphiphilic diblock copolymers of polylactide and polyethylene glycol. So polylactide presents a hydrophobic block, and polyethylene glycol is a hydrophilic. And well, these copolymers are able to self-assemble into various nanostructures, and the size and morphology of this nanostructure is dependent on the length of the block, and the composition of copolymer. So there are several ways to control the molecular structure. Molecular structure and architecture of these systems in order to control properties of the polymers and properties of the nanoparticles. So first we control the length of the blocks. Normally we fix the length of hydrophilic block and change the length of PLA block from tens of units of monomeric units up to thousands. Then we can change the toxicity either using L-lactide or D-L-lactide, which in turn affects the ability for this block to crystallize, and well, it also has effect on self-assembly, as I will show you. Also, we can introduce glycolide units in the hydrophobic block or caprolactone units in order to tune the degradation rate and the hydrophilicity of the block. Also, we can change the N groups, which can be hydroxy or carboxy. Another instrument to control the properties is an architecture of the copolymers. They can be linear diblock or triblock copolymers. They can be star-shaped and from having from 3 up to 8 arms, and also they can be even hyperbranch based on bolt-on. For example, dendritic polymers having up to 64 arms. Well, these branched systems are interesting in terms of a high number of end groups, which we can use to immobilize, for example, our anti-cancer agent or dye or something else. And also they have modified viscosity, usually lower viscosity at low concentration solutions, and also they have a modified, they can modify the release profile of the drug. So basically we have a lot of instruments in order to control the properties of the polymers and of the nanoparticles based on these polymers. Now let's talk about the synthesis. For synthesis of diblock copolymers, we use ring opening polymerization reaction, which is well known. Basically, the lactide ring is opening through the action of catalyst, which is stannous octanoate, and in presence of hydroxyl-containing compounds, the polymerization of lactide starts from the hydroxyl group, and this way we can polymerize the lactic acid block on the hydroxy group of the polyethylene glycol. If we have 2 hydroxyl groups, we can synthesize a triblock copolymer, having polyethylene glycol in the middle, and a polylactide block on the ends. In this case, the reaction is synthesis of diblock copolymer, and well, by changing the ratio of lactide to polyethylene glycol in reaction mixture, we can tune the length of lactide block. In this way, we present a lactide block which have a degree of polymerization from 30 units up to 240 units. We studied kinetics of reaction, and it was interesting that usually when we add a hydroxyl-containing co-initiator, the reaction accelerates, but in case of polyethylene glycol, we see that the higher content of polyethylene glycol, it is the shorter lactide block, we have the slowest reaction. And for the longest PLA blocks, we have the fastest reaction. So using these curves, we optimize the reaction conditions and synthesized a series of copolymers having high degree, equilibrium degree of conversion and predetermined length of lactide blocks. It is important not only to achieve high conversion, but also to prove that the block copolymer was formed indeed, which is normally not done in the literature. But here we can see the joint group of methylene on the NMR spectrum, and by calculating the number of protons of this group to a number of protons of N group of PLA block, we do confirm that the diblock copolymer is formed, and it has a diblock structure, and not, for example, a homopolymer of lactide, which can be formed if the synthesis starts not from hydroxyl group of polyethylene glycol, but from the impurities such as water or lactic acid units. That's an important issue, and that's why I'm talking a lot about it, because well, synthesis of well-defined copolymers is crucial for further investigations, and we do a lot of work to synthesize them and to prove that this structure is indeed what was targeted. So we changed the length of lactide block, and also we changed the nature of the tacticity using also the lactide. And in this case, we changed the molecular weight and degree of polymerization from 70 up to 1,400 units. So you can see that for lactide blocks which are shorter, we have a rather good polydispersity, but switching to higher molecular weight blocks, the dispersity becomes poor, and this is actually very hard to overcome. Also, we are looking for the biocompatible catalyst, a catalyst because the stannous is not the best option for biomedical applications. And here we propose to use organic DBU, diazo-bicycloundecene catalyst, which works well in solution at room temperature, and the reaction time is from 5 minutes up to 2 hours with excellent control over PDI. And well, you can see that the molecular weights and are well controlled, and also the polydispersity is very narrow. So this is one of the prospective catalysts which can be used for synthesis of such diblock and triblock copolymers. For synthesis of star-shaped polymers, we use a two-step procedure. Firstly, using the co-initiator with different number of hydroxyl groups, we prepared stars having 3, 4, or 6 arms of PLA. Well, the number of arms is determined by the number of hydroxyl groups in the co-initiator, and the length of each arm is determined by the ratio of lactide to co-initiator. At the second step, we conjugate the carboxylated polyethylene glycol to the stars, resulting in formation of star-shaped amphiphilic copolymers. We also studied kinetics of this reaction, and we have found an interesting result that the effect of co-initiator effect of the co-initiator concentration on the reaction rate is the opposite for 3-arm samples and for 6-arm samples. So the reaction tremendously slowed down for the 6-arm PLA having the shortest lactide block. So this is probably attributed to the steric hindrances, and that it was proved by low rate of conversion of hydroxyl groups of co-initiator in the reaction. So the structure of this polymers was also confirmed by NMR, and we synthesized a series of copolymers having 3, 6, and 4 arms, and use a number of methods to prove that they are indeed star-shaped, because we can also obtain linear comet-like or cycles as the side products of this reaction. But using NMR, MALDI-TOF, and GPC-based triple detection, we have proved that the structure is well controlled. So next, we performed the conjugation of these stars with a polyethylene glycol and synthesized a series of amphiphilic copolymers containing arms which consist of PLA block conjugated to the polyethylene glycol. block. So to summarize its synthesis part, we have changed the length of lactide block from 15 up to 100, 1,400 units. We used crystallizable poly-L lactide block and amorphous poly-D lactide block with a fixed length of PEG, which can be either 50 or 100 units, and change the architecture, diblock, triblock, and star shape with different length and number of arms. To prepare nanoparticles, we use different methods, but mostly we use nanoprecipitation, a well-known technique. Basically, we prepare an organic solution of copolymer in acetone and add water, pure water to this organic phase, which results in formation in self-assembly and formation of nanoparticles. And then we evaporate the solvent and obtain the water suspension and water dispersion of nanoparticles. We do not do any filtration or separation or fractionation of nanoparticles. And further, I will present the results on investigation without any kind of separation, because we think we should firstly get the most information about the system, and only after that we'll do the separation. So we use normally three techniques for studying our systems: dynamic light scattering, transmission electron microscopy, and also small angle X-ray scattering. Here the results of light scattering is presented. You can see the for the copolymers having DL lactide block with the length from 14 up to 70 units. We can observe the main fraction of nanoparticles with a size of 24 nanometers and a fraction of aggregates with a size of 100 nanometers and more. And well, this data is presented with the intensity of them. This is size distribution by intensity, and all of you know that the larger particles, they scatter much more intense, and actually the fraction of these aggregates is minor, and we can easily remove them by ultracentrifugation. And so the concentration of the dispersion almost don't change after this procedure. So basically, we get the nanoparticles of around 20 nanometers, and by transmission electron microscopy, so you can see that these spherical nanoparticles with a well-defined shape and diameter. So increase of the length of hydrophobic block leads to an increase in the size of nanoparticles, and they tend to aggregate. We still can separate them, but they are not able to freeze drying. And after freeze drying, this water dispersion, they just aggregate, and we can't use them for drug delivery. Anyway, we studied the effect even for longer blocks, and we can see that the size further increases up to 200 nanometers. And also for longer PLA blocks, we see the formation of at least two fractions for the longest PLA block, having size of 50 nanometers and 200 nanometers. Small angle X-ray scattering is a powerful technique to study this type of nanoparticles. Here you can see the scattering curves of aqueous dispersion of nanoparticles. And here is a form factor of nanoparticles, and using Fourier transform, we can get the pair distribution function. We can determine the Dmax from these functions, which corresponds to the size to hydrodynamic diameter of nanoparticles. Also, we can determine the radius of gyration and prove that the nanoparticles have the core corona structure. Well, as to nanoparticles fabricated from the amphiphilic copolymers having hydrophobic block, we can see also the two fractions, fraction of small nanoparticles and their aggregates. And using IFM and TEM, we studied them more precisely. And so we suppose that due to crystallization of the PLA block, the aggregation starts, and this crystallization is confirmed by the wide-angle X-ray scattering of photodispersion of micelles. Here you can see the break peaks corresponding to the crystalline alpha form of the PLA. Thus, we can suppose that we can confirm that the structure is also core corona, but these particles have a crystalline core, and probably just by aggregation of this cores, we get this aggregate, which are rather hard to separate. This crystallization also leads to formation of interesting morphologies, such as cylindrical, worm-like morphologies, rod-like morphologies, depending on the length of PLA block. These are beautiful structures, and we studied them in details, but particularly for drug delivery, well, they almost useless because it's very hard to control and to prevent the aggregation in different kinds of structures. For drug delivery, we need mostly spherical nanoparticles, which are easily freeze-dried and reconstituted. So next we studied star-shaped nanoparticles, which demonstrate also a minor fraction of aggregates and the size of around 10 nanometers. On the Sachs curve, you can see this curve is typical for the for one fraction of micelles, and here you can see the increased scattering in the low S region, which is attributed to the scattering of the aggregates. Well, to summarize the results of size of star-shaped nanoparticles, you can also see the transmission electron microscopy images, and well, they aggregate severely into various lamellar structures, rod-like structures, if the length of the PLA block is higher than 25. So for further experiments, we chose PLA block with a length of 10 units and 25 units. We can load various types of drugs, both hydrophilic and hydrophobic, inside these particles. And today I will focus on oxaliplatin, which is an anti-cancer drug, which is used for treatment mostly of colorectal cancer. And the preparation procedure was the same, but we solubilize the copolymer in the water phase, and then perform the nanoprecipitation. Here are the results of drug loading of the oxaliplatin into nanoparticles. You can see rather good, great, even encapsulation efficiency, which is close to 90 and 100%. And the drug loading was about 5%. Using Sachs, we have confirmed that oxaliplatin is present on the surface of nanoparticles, and the release of the oxaliplatin was quite fast, and you can see that after around 5 to 8 hours, both from the nanoparticles from linear copolymers and from star copolymers. All of the drug was released. So the cytotoxicity tests were performed on a series of various cells, and these are cancer cells, and these are normal. Well, you can see that the IC50 values were rather similar for oxaliplatin and for block copolymer nanoparticles, although some changes were observed on the normal cells, which is good because well, the IC50 values for normal cells were high. Next, we studied the cellular uptake of these nanoparticles, and here the results of flow cytometry demonstrate that there were no change in accumulation uptake from 1 to 6 hours. But using the confocal microscopy, we can see that after 1 hour, the nanoparticles are at the surface of the cells, and while after 4 hours of incubation, they are inside the cells. And now the preliminary results of in vivo experiment. We have used for this experiment free oxaliplatin nanoparticles based on linear and star-shaped oxaliplatin. And you can clearly see that the volume of the tumor was much lower both for the linear and the star-shaped nanoparticles loaded with oxaliplatin in comparison with a pure drug. And also this reflects in the tumor inhibition index, which was higher at all periods of times for linear and star-shaped nanoparticles. And these results are statistically significant. We have from this statistical analysis. So, and finally, I would like to summarize my talk with the question: which particles are better, the smaller or the larger? Normally, people say that the PLJ with the size of around 100 nanometers or 150 is the best. But actually, it's a trade-off between the tumor targeting, clearance rate, and background accumulation. And well, you can see that for larger particles, they indeed demonstrate the better tumor targeting and low clearance rate, but they accumulate well in many tissues and organs, which is opposite for the smaller particles. They almost can be found. They can be found in the background, but they have lower tumor targeting and high clearance rate. So basically, in this paper, which are not ours, but very interesting, the investigators showed that nanoparticles with a size of 12 nanometers can be a best choice. So, and finally, I would like to thank Russian Science Foundation for support and my colleagues who performed the experiments, and thank you for your attention.